In this video, we're going to have a look at how we can use exponential functions to model certain situations. So let's take a look at three examples. Our first one depicts bacteria growth. So we've got a culture of bacteria that the initial population contains 50 cells, and every hour the number of bacteria are doubling. So when we start looking at a table of values, we've got the time of hours going up by 1 and a population. So after 1 hour, we can see that our population has been multiplied by 2. So after 2 hours, we've got a population of 200. After 3 hours, that's doubled to 400. And after 4 hours, that's doubled to 800. And this will continue. So now what we want to do is focus on deriving a general rule to represent this bacteria growth. So thinking about for any time in t hours in our example. So thinking back to exponential functions, we initially were using y equals k times a to the x to represent an exponential, where k was our initial value and a was our multiplying factor. When we're talking about populations of growth and decay, we tend to use some letters to represent it. So I'm going to use p for population here instead of y. And instead of our initial value being k, I'm going to denote that by p with a subscript of a little o, saying population at time 0, or p0. I'm still going to use the a as my multiplying factor, and instead of x, we've got t as our variable here. So we're going to use this idea when we're discussing situations of growth and decay. So knowing that my initial population is going to be p0 at 50, my multiplying factor is 2, that's my a value, I can form a rule that says the population is represented by 50 times 2 to the power of t. So using this formula, we want to determine the population after 12 hours. So this is when t is 12. So we can substitute 12 into the rule that we have constructed, and we can work out that we're going to have 204,800 bacteria present after 12 hours. So now let's look at our second example, which is to do with investments. Now this looks very familiar because we've dealt with compound interest before. So we've got $1,000 is deposited into an account. It earns 5% interest per annum or per year, and we're rolling that over or compounding that annually, which means once a year. And they generally do that at the end of the year or the time period. So if we have a look, we've got to think that we've got a growth here. So our a value that we're going to use in our formula obviously has to be larger than 1, because we want the one whole of $1,000 plus 5% more. 5% is a decimal 0.05. So we can combine that to make our a value of 1.05. And we can see already that in our table we've times by 1.05 to get from 1,000 to 1,050. So if we keep doing that, after 2 years, we should have $1,102.50. After 3 years, we'll have $1,157.63, rounding to 2 decimal places. After 4 years, we'll have $1,215.51, and we can keep this going. So we can derive a general rule for this. We're going to use V for our investment value. It's accumulated amount. So we want the initial value, which we could call value V0 if we wanted to, times our rate that we've got, our multiplying factor, which is a to the power of t. So our rule can say V equals initial value of 1,000 times 1.05 to the power of t. That reminds me very much of a simplified compound interest formula. So the value of this investment after 20 years, so we can just sub in t as 20, and we would come out with $2,653.30. So how many years would it take for this investment to double? So this is just finding the value of t, knowing the value has become 2,000. So if we substitute 2,000 into our formula, we could use our class pad to solve for t. In doing so, we could, by hand, we could divide by 1,000. So essentially, we could simplify our formula to be 2 equals 1.05 to the power of t. And in solving this, we get t is 14.21. So what we need to do is think about when this investment matures, when will we see that doubling happen? So this would be, because we're talking, after 1 year, we have $1,050, and after 4 years, we have $1,215.51. After 14 years, we wouldn't actually quite have doubled our investment. So it would have to be after 15 years. And another way of looking at this is to think about the table of the value of t to the value of an investment. If we put in t as 14, we'd end up with $1,979.93. So it's not until the 15th year where we see that we have gone over that double mark. So there's no description here to say to the nearest month or to the nearest 6 months. We would say after 15 years. In our last example, we're going to have a look at a very simple depreciation. So a car that was bought for $25,000 is now depreciating by 10.5% every year. So we're going to complete a table of values. But what we notice about this table of values, we're looking at the value of the car after each year. So this is actually the value that the car retains, not about the 10.5% that it's losing. So if this car is decreasing by 10.5%, it means that it is going to retain 89.5% of its value. So if we think about this in terms of an exponential function, the value of the car, initially worth $25,000, we're now going to say, okay, the A value we're going to have here has got to be less than 1, greater than 0, but we want the percentage that retains. And as a decimal, that's 0.895 every year. And we can simply now multiply times 0.895 to find the future values. So we can see that the car slowly depreciates its value. And that will continue. So your task is to have a go at page 2 and have a look at the 3 examples, one on half-life, one on population growth, and one on population decline. Looking at these table values or completing the table of values, be able to form an equation to represent the situation and see if we can calculate some of the values.